Hello friends, this is part 2 of solved question paper mathematical physics PHYC3A third semester, okay, 2024, Dibrugarh University. So before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. So in part 1 we have solved up to question number from question number 1A to question number 2A. Now today we're going to start from question number 2B. Okay, if you want to follow me on Insta, this is my Insta ID, OJHALAKHYAZIT 123. That's my Insta ID. You can follow me on Insta. So now let's start. So here you see, find the Jacobian of if r is a function of x is a function of r comma theta, which is equal to r cos theta, and y is equal to r sin theta. Right, now you see, what do you mean by Jacobian? First let me write here, just give me a second. Now you see, if u is a function of x comma y and v is also a function of x comma y, okay, then their Jacobian is given by the determinant of del u by del x, so del v by del x, then del u del y, and del v by del y. So this is the Jacobian of these two functions. Okay, here we have solution. Here x, that is function of r comma theta, which is equal to r cos theta, and y, which is a function of r comma theta, then and it is r sin theta. So here you see, instead of u and v we have x and y, and instead of x and y, here you see that I have written here, instead of x and y we have r and theta. So we can write this way, we can write this way. Let me show you, just give me a second. If x is a function of r comma theta and y is a function of r comma theta, then Jacobian of this r comma theta will be given by determinant del x by del r, del y by del r, and del x by del theta, and del y by del theta. Okay, that's how we can obtain. So first let us obtain this derivative. So del x by del r, that's gonna give you, if you differentiate this with respect to r, then you're gonna get cos theta, right? Then that's fine. Del x by del theta, if you differentiate this with respect to theta, then del x by del theta, that's gonna give you minus r sin theta. Derivative of cos theta is minus sin theta, right? So because now this cos theta is the function of theta, so if we are differentiating with respect to theta partially, then we should get sin theta, taking r as constant, as it is partial derivative, right? So similarly we can find del y by del r. Let's differentiate this, taking this part as constant, because we are differentiating with respect to r now, right? So then we're gonna get sin theta, then del y by del theta. Now take r as constant, then sin theta, differentiate sin theta with respect to theta, then it's gonna give you cos theta, right? That's gonna give you cos theta. So hope you have understood this. Sorry, r cos theta, not only cos theta, r cos theta, r cos theta. Okay, now let's find the determinant. Okay, now let me clean this side. Okay, so here, okay, let me solve the remaining part here. So we need to find the Jacobian. Therefore the Jacobian there r comma theta is given by determinant. So this and okay, let me write this one here. So now let's put the values here. So del x by del r is nothing but cos theta, right? And del x by del theta is minus r sin theta, right? Let me write it properly, minus r sin theta, okay, minus r sin theta. Then del y by del r is sin theta, so let me write here sin theta, okay. Then del y by del theta is r cos theta, so here it is r cos theta, okay. So hope you know how to find the determinant, okay. This one into this one, that's gonna give you r cos square theta minus this one into this one. There is already one more minus, right? So minus this is gonna be plus, so r sin square theta, and r is taken common, we're gonna get cos square theta plus sin square theta, so that's gonna be equal to 1. So r into 1 is simply r. So this is the answer. So hope you have understood this. So now let's move on to the next question. So here you see, how can Dirac delta function be represented as limit of rectangular function? So now you see, let me show you how to find the how to express the Dirac delta function as rectangular function. Suppose we have a rectangular function. Now you see, rectangular function. So let me first represent it by graph, okay. First let's represent it by graph. So here it is r sigma, which is a function of x. This is x, and now you see, suppose let us consider a rectangle, okay, like this, okay. Now you see, this point is suppose x comma a, this point is x comma a, okay. And let me consider width of this box is suppose 2 epsilon, okay, so that we can write this point is x is equal to a comma minus phi, minus a minus epsilon, and this point we can write x is equal to a plus epsilon, okay. And its height is 1 by 2 epsilon, okay, 1 by 2 epsilon. So now you see, so how to write this function? So let me split the screen into 3 parts, okay. So how to write this function? So here we're going to write this function in this way, r sigma of x. So let me write this one here, okay, is equal to 1 by 2 epsilon when, you know, so just give me a second, okay, just give me a second, just wait. Let me write this function here. First let me write this graph, draw this graph here. Just give me a second. Let me find some space here, okay. Now you see what we can do. This function, this rectangular function, this can be defined as this r of x, r sigma of x is equal to 1 by 2 epsilon when this x is greater than a minus epsilon and x is less than a plus epsilon. That means when the value of x is lying between a minus epsilon and a plus epsilon, then this value of this function is 1 by 2 epsilon, and out of this region it is equal to 0 if x is less than a minus epsilon and x is greater than a plus epsilon, right? In these two cases this is equal to 0, right? So hope you have understood this definition of this function. So now you see here you see, if epsilon tends to 0, so here you can see that clearly, if when epsilon tends to 0, this is going to be 1 by 0. This is going to be 1 by 2 into 0. That means 1 by 0, which is going to be again infinity. So in that case, this function r sigma of x then tends to infinity, right? When epsilon tends to 0. Okay, and if you take the integral minus infinity to plus infinity r sigma of x dx, okay, then you can split this into three parts. One is from minus infinity to this point, x is equal to a minus epsilon, then a plus epsilon to plus infinity, then a minus epsilon to a plus epsilon. That means, let me show you this integration. This part gives the area below the curve, right? When you integrate it from minus infinity to plus infinity, then what you gonna have, right? Then what you gonna have, let me show you. Now you see, this is the graph. Let me draw it roughly. So this point is a minus epsilon and this point is a plus epsilon, and towards right you're gonna have plus infinity and towards left you're gonna have minus infinity. So we can divide this into three integrals. We can express as sum of three integrals, as one from minus to this minus infinity to a minus epsilon, that is r of x, r sigma of x dx. Then another one is then this part, a minus epsilon to a plus epsilon, then r sigma of x dx. Then third part is from a plus epsilon to plus infinity. So let me write it properly. Let me clean this first. So third part is a plus epsilon to plus infinity r sigma of x dx. Now from this graph you can see that from minus infinity to this point, a minus epsilon, the value of this function is 0. The graph starts the graph touches this height at this point. Okay, so here it is 0. You can see the graph like this. This is the graph of the function, right? And this region here, from minus infinity to a minus epsilon, and from a plus epsilon to plus infinity, this region, okay, the value of r sigma of x is equal to 0. Here also, only in this region its value is 1 by 2 epsilon, right? Hope you have understood this. So that's why we're gonna get the value of these two integral, we're gonna get 0, right? Hope you have understood this. Then integration from minus a minus epsilon to a plus epsilon, then r sigma of x in this region is nothing but this 1 by 2 epsilon. So let me put here 1 by 2 epsilon dx, right? That's what we're gonna have. So therefore now value of this integral will be now, therefore integration minus infinity to plus infinity r sigma of x dx, that is equal to, this part is constant, so we can take it out of the integral, then minus integration from minus a minus epsilon, not minus, a minus epsilon to a plus epsilon dx, right? So that's gonna give you integration of dx is x, and the integrating limit is a minus epsilon to a plus epsilon. Let's put the lower and upper limit. Then upper limit is a plus epsilon minus lower limit is a minus epsilon. Because of this minus, this sign will be plus. So here minus a plus a gone, so we end up getting 2 epsilon into epsilon plus epsilon, again 2 epsilon, and these two cancels, it's gonna give you 1. So that's why we got the value of this integration is equal to 1. This is equal to 1. Now you see, this is the property of Dirac delta function. Let me show you in the next slide. First let me copy the definition of this rectangular function. Let me copy this, just give me a second. This is supposed to be sigma, okay, sorry, not sigma, epsilon. Okay, so let me take a new slide. This is the new slide. Now you see, you don't need to repeat these things again, as I have changed the slide and I don't want to go back to the previous slide again and again. So that's why I have written these 3 points again. Okay, you don't need to repeat this. Okay, once you have written, that's enough. So now you see, let's discuss the Dirac delta function now. Dirac delta function. So now Dirac delta function is defined this way. So x delta x minus a is equal to, it's gonna be infinity if x is equal to a, and it's gonna be 0 if x is not equal to a. So let me explain it graphically. Now you see, suppose this is x, this is the delta function. Now you see, suppose you have a rectangle like this. Okay, this is a rectangle. So you have another rectangle, okay, and you have another rectangle like this. Now you see, suppose its rectangle that I have drawn here, area bounded by this rectangle is suppose 1, is always 1, right? Suppose this is a rectangle, and if you reduce its width, okay, but if you don't want to if you don't want to reduce the area, but if you reduce this width, then this height must be increased so that area remains same. Similarly, if you want to reduce more, then its height gonna be increasing again so that area remains the same, that is equal to 1 in case of the Dirac delta function. Okay, I will explain it. So if you reduce the width to a very, very small value, then height of this rectangle will tend to infinity. Okay, right? Then only the area will be equal to 1. Let me show you something. Okay, so this is a rectangle. Suppose its area is equal to 1. Suppose if you reduce the width of this rectangle. Okay, then if you want to keep the area same 1, so then height must be increased. Now its area is 1. Okay, now if you keep reducing this width, but if you want to, that means width almost tends to 0. Width of this rectangle is suppose tends to 0. So let me consider the width is 2 epsilon now. If epsilon tends to 0, then this must be infinity. Okay, this must be infinity. And right, hope you can understand. Hope you can understand what I am trying to explain. Now you see, suppose this is the graph. This is x, this is delta. Okay, now this point is, suppose x is equal to a, right? X is equal to a. Sorry. Right. So here you see, here this delta of x minus a, this is equal to nothing but infinity. Okay, at this point, at x is equal to a, this function delta x minus a is infinity. Okay, and at other points where x is not equal to a, its value is 0. Okay, so hope you have understood this. Now if you consider the graph of the rectangular function, right? Now if you consider the graph of the rectangular function, this is the graph of, suppose graph of the rectangular function. Let me show you here. Okay, so this point is x is equal to a. Okay, this is x-axis, here the rectangular function. So now you see, this point was a minus epsilon and this point was a plus epsilon. Okay, and when this epsilon tends to 0, okay, when this epsilon tends to 0, then this point will be very close to x is equal to a. Similarly, this point will be also very close to this point x is equal to a, right? So we can write as epsilon tends to 0, then x tends to a, right? Because this point x is equal to a minus epsilon, that tends to 0, that tends to a, right? So suppose x is equal to, in case of x is equal to a minus epsilon and x is equal to a plus epsilon, in both cases, if epsilon tends to 0, then x tends to a, right? If it is equal to 0, then x will be equal to a, right? Hope you have understood this logic. And if x tends to a, then we can say that r sigma tends to infinity, right? R sigma tends to infinity, because as I have already, we have already seen this function. Here you see, if epsilon tends to 0, then obviously 1 by 2 epsilon, that's going to be infinity for epsilon is equal to 0, right? So that's why this function tends to infinity when epsilon tends to 0, right? So hope you have understood this. So if that is the case, then we can say that when x tends to a, you see, when x is equal to a, then it becomes infinity, right? So when x tends to a, then we can say delta x minus a tends to infinity as well. So that's why we can say that this function becomes equal to infinity, when x is equal to a, so we can say this is nothing but a limiting case, that is delta x minus a is equal to limit x tends to a of this rectangular function, right? So when x tends to a, epsilon tends to 0. When epsilon tends to 0, then r tends to infinity, right? And when x tends to a, this delta tends to a also tends to, delta of x minus a also tends to infinity, right? So hope you have understood this. So we can express this Dirac delta function as a limiting case of rectangular function. So hope you have understood this. Now let's move on to the next question number 2D. Okay, here you see, if u1, u2, u3 represents the coordinates h1, h2, h3 are the scale factor for 3D curvilinear coordinate system, then what are the values of these three and these three for the spherical coordinate? So now you see, suppose this is x, y and z axis. Suppose x, y and z axis. This is the y axis, this is z axis, this is x axis. Okay, and here you see we have a point here. This point is suppose P with coordinate x comma y comma z. This is origin O. OP makes angle theta with z axis, and this is the perpendicular from this point to the z axis. Suppose this is the perpendicular from P on z axis, and let me draw another perpendicular on xy plane. Okay, so this is perpendicular on xy plane. Let me join this. So here you see these two are parallel and equal. Okay, so though diagram is not perfect in this 2D plane, okay, consider that way. So this is perpendicular on this plane. These two are also perpendiculars on x and y axis. Okay, so this angle is suppose phi. So if this is x, y, z coordinate, then you see this point, this length is x, so this gonna be also length. This length gonna be also x, and this cuts at y. This is y, so this length gonna be also y. Now you see, let me consider this OP is equal to r. Okay, so here you see u1, u2, and u3 represent the coordinates and h1, h2 and h3 the scale factors of suppose a point P, x comma y comma z. Okay, for the curvilinear 3D curvilinear coordinate system. Okay, so as shown in the figure here, you see u1 is equal to r, u2 is equal to theta, and u3 is equal to phi. Okay, so then x coordinate will be equal to, the x coordinate will be equal to, now you see this x coordinate, this one. So if this is r, if you consider this right angle triangle, then you see, first let me find this perpendicular. Suppose this is PQ, this is suppose PM. Okay, so first let me find PM. from this triangle, what you're gonna get from this triangle OPM, you don't need to write this part, okay? Just let me show how we have got all this coordinate x comma y comma z, okay? So from this triangle you're gonna get sine theta is equal to perpendicular PM by hypotenuse is equal to r, that is OP, right? PM by r, so PM gonna be equal to r sine theta. So if PM is r sine theta, then QO is also r sine theta, because these two are equal, okay, and parallel as well, though it is not seems to be parallel in this diagram, because in 2D plane it is difficult to draw this figure. This is 3-dimensional, right? So just remember that this OQ is r sine theta, and cos theta will be equal to OM base by hypotenuse, that is small r, hypotenuse is small r, so OM equal to r cos theta. So this OM is equal to r cos theta, okay? So now you see this x, you see this is perpendicular again, and if this is x, this is also x, okay, this is also x. So from this triangle you can see, from this triangle, this is right angle, this is right angle, right? This is phi. So from this triangle we're gonna have that sine phi is equal to, so here not sine phi, cos phi is equal to this x by the hypotenuse. For this triangle, hypotenuse is OQ. Here the OQ is nothing but r sine theta, so r sine theta. So therefore x coordinate will be equal to r sine theta cos phi, right? Hope you have understood this. Now you see, let me clean this. Now you see y from this triangle, if you consider this phi, then y should be taken as perpendicular. So let's find sine phi. Here perpendicular is y, hypotenuse is again OQ, which is equal to r sine theta. So that's why y coordinate will be equal to r sine theta sine phi, and z coordinate, this is z coordinate, which is equal to OM, that is nothing but, you know, r cos theta. That's what we have got. So now let me copy this information that we have got now, and let me go to a new slide, okay, so that I can explain. So from here we have got this U1, U2. Here we have got U1, U2 and U3. Now let's find the H1, H2, H3. Okay, here you see H1 will be given by mod of del R by R, del R vector by del R, and H2 will be given by mod of del R vector by del theta. Then H3 gonna be again del R vector by del phi. Okay, first let me find what is R. So R is nothing but the position vector of the point P. This vector, this if you write this position vector R, if its coordinate is x comma y comma z, then position vector R vector will be given by x I cap plus y j cap plus z k cap, right? Hope you have understood this. So this is x I cap plus y j cap plus z k cap. Now let me use these spherical coordinates. So here you see r sine theta cos phi instead of x, r sine theta sine phi, it's supposed to be sine phi, okay, this should be sine phi, right? And instead of that we're gonna write r cos theta, okay? So let me write this. If we use these values, let me copy all these values, okay. So let's replace the x by r sine theta cos phi I cap, plus let us replace this y by r cos theta, sorry not cos theta, sine theta sine phi, then plus, sorry not plus, j cap, there should be a j cap, plus then z is replaced by r cos theta, and we must write the k cap. Okay, so hope you have understood this. Now you see, let's find this derivative. Let me differentiate r vector with respect to r. Then what we're gonna have, we are differentiating partially, so we're gonna, when we differentiate with respect to r, then we're gonna consider r as variable only, and this part will be taken as constant. Similarly, same procedure should be applied here and here also, right? Hope understood this. So if you differentiate r with respect to r, that's going to be 1, so sine theta into cos phi I cap. Then similarly here, these are going to be equal to 1, so we're going to get sine theta sine phi j cap, plus if you differentiate this r, that's going to be again 1 into cos theta is cos theta k cap. So let's find the magnitude. Okay, first just let me find all the derivative. Again, if you differentiate r vector with respect to theta, then what you're gonna get, you're gonna consider this part as variable only, theta is the variable only, and phi and r to be taken as constant this time. So then derivative of sine theta is cos theta, so we're gonna get r cos theta cos phi I cap, and derivative of again sine theta is cos theta, so r cos theta sine phi j cap, and plus derivative of cos theta is minus sine theta, so here we're gonna write minus r sine theta k cap. Similarly, let's differentiate r vector with respect to phi, so this time we're gonna consider phi as constant rather r and theta. Okay, so instead of r and theta, we're going to take phi as constant now, this phi as constant. So here you see, sorry not phi as constant, phi is to be taken as only variable this time, so other parts are constant. Okay, so here r sine theta, if you differentiate cos phi, then you're gonna get minus sine phi I cap. Then if you differentiate sine phi, then you're gonna get cos phi. Then if you differentiate this, there is no phi, so it's gonna be 0. That's what we have got, right? 0 k cap. It's supposed to be j cap. Okay, now let's find the mod of this. So that is h1, which is gonna be equal to mod of this. So how to find the mod? Hope you know this. So just sum of the squares of the coefficient of I cap and j cap and k cap, right? So sine square theta. So here you see, here we're gonna get sine square theta. Here also we're gonna get sine square theta, which can be taken as common. Then after taking this sine square theta common, we're gonna left with cos square phi and sine square phi within bracket, cos square phi I cap plus sine square phi j cap, then plus, then square of cos square theta k cap, right? So now you see, this is going to be equal to 1. Then again we're going to get sine square theta plus cos square theta, right? Here we don't need to write the k cap, j cap, I cap, okay, because we are calculating mod, okay, modulus, magnitude only. So now if this become equal to 1, then again we're going to left with sine square theta plus cos square theta, that's going to be again 1. So that's why this value of h1, this value of h1 is equal to 1. So value of h1, that's going to be equal to 1. So we have got h1. Now let's find the h2. h2 will be equal to mod of this one, right? h2 will be equal to, let me go to the next slide. Okay, let me go back to the previous slide. H3 is mod of this, right? So let me copy this and let me go to the next slide. Okay, here you see H3, that's going to be mod of this. So its modulus, again same procedure, minus r sine theta sine phi, this square, plus r sine theta cos phi, again square. So square of this will be equal to r square, negative will be positive, sine square theta. From both we can take sine square theta common, right? And within bracket we're gonna get sine square phi plus cos square phi, and that's gonna give you, here you see this part become 1, so we're gonna get r square sine square theta. So square root of this r sine theta. So this is the H3. So hope you have understood this, how to find H1, H2 and H3. So now let's move on to the next question. So this is question number 2E. Using the properties of Dirac delta function, let me evaluate this. So which property we're going to use? We're going to use this property, that integration minus infinity to plus infinity function of t, and we have Dirac delta function here, t minus a, and dt, that's always going to be equal to f of a, right? So we're going to use that property here. So what we have here, you see, integration minus infinity to plus infinity e to the power minus 5t delta t minus 2 dt, that's what we have. So here you see, here our f of t is nothing but e to the power minus 5t, this is okay, and a is equal to this, t minus a is equal to t minus 2 here, so a will be equal to 2. So according to this property, so we know that according to this property, replace this f of t by this one, right? So what we're gonna get, integration minus infinity to plus infinity, f of t is nothing but e to the power minus 5t, then t minus here delta, t minus a means t minus 2 here in this case dt, so that's supposed to be equal to, here a is equal to 2, so it's supposed to be f of 2. So f of 2, since f of t is equal to this one, so f of 2 must be equal to e to the power minus 5 into 2, so that's going to be e to the power minus 10. E to the power minus 10 means 1 by e to the power 10. So that is what we need to find, right? Hope you have understood this. So remaining questions will be solved in the next video. Bye bye, see you in the next video.